Hello everyone, I am Sara Sasaninejad from SMEX Group in Tallinn Department of Ghent University. I want to present our work about a system content analysis for a two-class queue where service times in a busy period depend on the presence of class 2. Now, why this topic? Imagine a road traffic like this image that you can see here. As you can see, in direction 1 there is no heavy vehicle, bus or freight and so on. On the contrary, in direction 2 we see heavy vehicles like buses. In the first direction, all the regular vehicles or cars can move with a regular speed. On the contrary, in direction 2 we see that the presence of these heavy vehicles on the road causes the other vehicles to slow down and move with a slower speed. So we can say that the presence of these heavy vehicles in direction 2 during an ongoing busy period can change the service time of all vehicles, and it will last until the system becomes empty. So motivated by this issue, we went through the related literature, and we have seen that in the related studies, the researchers have used queuing theory to address the uncertainties of real-world phenomena, and also they have used multi-class queuing model to address the non-identical behavior of customers. And we have seen in the related literature, in multi-class queuing system, various classes of customers can also receive different treatments. And we saw this research gap in the related literature that there has not been a model that considers the interdependency between the service time distribution of different classes of customers. So in our model, we have tried to consider a special kind of service time specification to take into account this interdependency. We will go through it further. And in our model, we have defined a two-class queuing system, namely class 1 and class 2 customer, with an infinite capacity single server. Our system is defined in discrete time domain that serves the customers in a first-come, first-served order. The random variable oj car represents the number of arrivals of class J customer in the kth slot, and the number of customer arrivals of both classes of customers are assumed to be independent and identically distributed with a general PGF. You see the joint PMF of the arrivals and the joint PGF of the arrivals here in these relations. But what about the service time distribution in our model? Service time depends on the presence of class 2 customer during an ongoing busy period. In this image, we imagine a busy period in our model. As you can see in slot K, we have arrival only from class 1 customers. And because of this, in slot K plus 1, we again consider S1Z as the service time for all the customers. But we see in the slot K plus 1, we have arrivals from class 2 customer as well. So in slot K plus 2, the service time distribution changed to S2Z. In other words, as there is no class 2 customer in our system, all service times will remain S1Z. And as soon as we have the first class 2 customer arrival, the service time in the upcoming slot changes to S2Z, and it will remain S2 until system becomes empty. So, in order to develop a 3D Markovian state description of our queuing system, we introduced 3 auxiliary random variables. Random variable xk, which is the total number of customers in the system at the beginning of a slot K. Random variable rk, which is the remaining service time of the in-service customer at the beginning of a slot K. Rk equals 0 if xk equals 0. and IK as the indicator of having had a class 2 customer in our system. IK equals 1 if during an ongoing busy period there is or has already been at least one class 2 customer in the system at the beginning of a slot K, and IK equals 0 otherwise. So, we can establish a set of system equations that describe the relationship between vector IK, RK, XK, and IK plus 1, RK plus 1, and XK plus 1. Depending on the values of XK, RK, and IK, we can distinguish 5 different cases. In case IK equals 0, in order to find the value of IK plus 1, we should see the variable R2K, or the number of class 2 customers that arrive in a slot K. If it's equal to 0, then IK plus 1 equals 0 as well. But in case that R2K is bigger than 0, then IK plus 1 equals 1. And in case IK equals 1, first we look at the number of customers at the beginning of a slot K. If it's bigger than 0, then we can say IK plus 1 equals 1. Otherwise, we should see the number of arrival of class 2 customers. If it's bigger than 0, then IK plus 1 equals 1. Otherwise, IK plus 1 equals 0. Now we define the joint PGF of RK and XK by PK XZ and in this relation. And the partial PGF PIK XZ, which shows us the joint PGF of XK and RK in different cases of IK, and it's defined by these relations. We know that PK XZ, or the joint PGF of XK and RK, equals to the joint PGF of, in case IK equals 0, and plus in the joint PGF of RK and XK in case IK equals 1. And we know this relation that we had it before in the previous slide. And we want to find the joint PGF of RK and XK in a slot K plus 1 in case IK equals 0 and IK equals 1 based on P0K and P1K. We have defined these relations in this relation equation 1. We have defined this FIK to simplify our model, our calculations, let's say, our calculations. As you can see here, P0K plus 1 is based on the relations for slot K. And here we have a relation for P1K plus 1, which is again based on the values in slot K. In a steady state, PIK and FIK for I equals 0 and 1 converges to limiting functions, which we have here. Then under the steady state distribution, stationary distribution, the equations 1 and 2 can simplify to 3 and 4. As you can see in previous slides, we have F1Z, F0Z as unknown functions, and P00, P100, and F00 and F10 as the unknown constant that should still be determined. So first we apply this relationship to find the relationship for P00, P000, or the empty system content, empty joint probability function in case of IK equals 0, and also for P100. Then we know the partial PGF of P0xz and P1xz should be bounded for all possible values of xz, then we can find f0z and f1z. And finally, by applying normalization, we find, and using the fact that xz must be bounded for all possible values of z, we can find fz0 and f10. So we can find all the unknown functions and unknown constant variables in our calculations. Then we have some numerical example to see the impact of considering this kind of interdependency between service times. We assume that the number of customer arrivals follow a Bernoulli distribution with lambda as their total arrival rate. We assume that alpha is the probability that an arriving customer is a class 2 and 1 minus alpha is the probability that an arriving customer belongs to class 1. The joint PGF Z1, Z2 in this case simplifies to these relations that you can see here. So, in order to show the effects of these parameters on the average number of customers in the system, we have two figures. We have developed two figures, this figure and this figure. And first figure illustrates the changes of the average number of customers in the system with respect to the arrival rate. In case S1 equals 1, S2 equals 2, and also in case S1 equals 2 and S2 equals 1. And this figure presents the changes of the average system content with respect to the parameter alpha in case S1 equals 1, S2 equals 2, S2, and in case S1 equals 2 and S2 equals 1. It is trivial that the average number of customers in the system increases in case of higher arrival rate, as we expected. And in part A of these figures, that is the case that the service times are twice as long as when at least we have one class 2 customer during our ongoing busy period. We see that a higher alpha as a higher lambda causes an increase in the average number of customers in the system, and it is good to mention that a higher alpha means that a higher probability of having had a class 2 customer in the system during the ongoing busy period. On the contrary, in case S1 equals 2, S2 equals 1, which means that the service times are longer when no class 2 customers have been present in the system. So a higher alpha leads to typically a shorter service time for more customers. Therefore, we see a lower average system content for higher alpha. Then we have this comparison. We compare our results with a conventional model in which service times of different classes of customers are independent and completely attached to the customer classes. As we can see, in case S1 equals 1, S2 equals 1, 2, and in case S1 equals 1 and S2 equals 5. So, what is the conclusion that we have here? The effect of considering the interdependency when alpha equals 0 or 1, we can see this effect vanishes. Both models have the same results. But when alpha is something between 0 and 1, our developed model shows higher average system content compared to the conventional model. And also, in this case, as the ratio of S2 to S1 increases, the mentioned differences becomes more tangible. So, in case that alpha is something between 0 and 1, considering this interdependency shows more real results. And we should consider this interdependency. Thank you for listening and your attention.